this, I think, is number 27 on the homework, and basically you're given a configuration like this. There's friction. I don't think I have the angle here. Let me turn on my pins. And this theta here is equal to 40 degrees, I believe. But you're given that MA is 102 newtons, MB is 32 newtons, and then you have all these situations. In the A situation, they want to know what happens if you just let go and it starts from rest. In other words, initially at rest. Well, some things we know that won't change, that we can find. We know that the normal force is equal to mg cosine of the angle, so that'd be, we're talking about this one right here because this 32 Newton one doesn't have a normal force. That's going to be 102 times cosine of 40, and that's going to give me basically 78. And then we already know the weight, or the force of gravity, is 102. We know that the force of kinetic friction isn't going to change. That's going to be mu k times the normal force. And if you take 0.25 times 78, you're going to get 19.5. That won't change. The direction will change, but the amount of friction will not change. And then they tell us that the static friction, which is the coefficient of static friction times normal force, you're going to take 0.56 times 78, and you're going to get, hold on a minute, let me do 19.5, and then this one you're going to get 44 newtons. Now here's the interesting thing about static friction. Static friction can be up to 44. It cannot be over 44, but it can be less than 44. So basically it ranges from 0 to 44 depending on what's happening. Kinetic friction is after it's moving, and it's always going to be 19.5. If we just look at a graph of friction over a certain time period, we put time down here, and you're pulling on something, not moving, not moving, not moving, not moving. When it gets to 44 newtons, in this case, it's going to break loose, and then it's going to go to kinetic friction, and that's always 19.5 newtons. So to begin with, the most the tension can be is 32 if it's not moving. So when we start it from rest, we know that this tension is going to equal 32 newtons. Now, tension can vary if it's accelerating, but when it's at rest, T is equal to 32. That's the A part, at rest. Well, something else that's not going to change is the force of gravity that pulls this downhill. And that's going to be mg sine theta. So if you take 102 times sine of 40, you get 66 newtons. Now, without putting any friction on here, which direction is this block going to try to move? It's going to try to be moving downhill, which means friction always opposes motion. That the static frictional force is going to be up this direction, and it can be up to, so I could say less than or equal to 44 newtons. Well, it's not going to move because if it was at its maximum value, 32 plus 44 is 76. Friction can't be larger. Friction can't make the upward force larger than 66, but it can make it at least 66. So because this can be less than or equal to 44, therefore it's not going to move. So the A part is A equals 0. That's the A part. That's the A part. Okay, I'm going to erase some of this stuff. You guys kind of keep a mental note here, write this down. Normal force isn't going to change. The frictional The kinetic and the frictional static isn't going to change. Those are going to be the same. So just so I can work out things, I'm going to erase these now because they don't change. And the B part says, what if I push it uphill? So the B part, what if I give it a shove uphill? So initially I push it uphill. Well, that changes the direction of the friction. And it also, we don't necessarily know the tensional force. If I push it uphill, I know for certain that downhill, it's moving, it's not static anymore. I know this is kinetic friction, which we've already figured out is 19.5 newtons. So if I push it uphill, I've got a total downhill force of 85. So let's just work this out. So if I look at this block right here, it's going to be, and I'm going to say up is positive, T minus 19.5 minus 66 equals negative 10.2 A. And I'm going to show you why this is negative in a minute. T minus 32 equals positive 3.2 A. That's the equation, sum of the forces equals MA. So I'm just summing up all the forces, subtracting the ones that are downhill, and then this one's positive, so it's going to be T minus the two downhill ones. If I add these two together, I get a total of 85.5 newtons downhill. So what I'm going to do is I'm going to subtract this equation from the top equation. When I do that, the tensions go away. They're 0. I get negative 53.5 newtons here. And I get negative 13.4 kilograms here times A. Well, if I divide both sides, I get A equal to 3.9 meters per second squared. But which direction is that acceleration? Well, first of all, something that's always going to happen, this always happens. The masses of a system always add together. If you're ever subtracting these two, then something's wrong, because you never subtract the two masses. This mass is 3.2 kilograms. This mass is 10.2 kilograms. The total mass of the system is 13.4 kilograms. So if I didn't make this 10.2 negative, then that means I would subtract these two. What that means, it means that this acceleration is downhill. It's downhill. So if you're doing this and you would have made this positive, and then when you subtracted this one out, 3.2 was positive, we were saying it goes uphill. You would have subtracted those two and you would have gotten a smaller number than 13.4. The mass never cancels. Masses always add together. So if you get one of these equations and the two masses are opposite signs when you subtract the two equations, in other words, if you're not combining your masses, something's wrong. Something's wrong. So that's always going to be true. So this is going to be downhill. And if we obey what the book says, it says put it in dot, or not dot, let me read it here. It says put it in unit vector notation. Well, that's just going to be negative 3.9 meters per second squared, and then you're going to say I. That's it. So very tricky, very tricky. Basically what you're going to do is you push this uphill and it slows down and stops. It doesn't move. Push it uphill, it slows down. If it's slowing down, the acceleration's to the left, not to the right. So in other words, this is going to go down, but it's going to slow down, and stop. That's what's going to happen if you push this thing uphill. There's just too much There's just too large of a gravitational force pulling it downhill for it to keep going uphill. This 32 newtons is not big enough. It's not big enough. So now the last question, and I'm going to erase all this stuff. The last question is, what if I give it a shove downhill? What happens? What happens if I give it a shove downhill? Well, you know what? That's the direction it kind of wants to move anyway, so that's going to do something for us there. So I still have T here. I still have 66. That hasn't changed. But guess what? If I push it downhill, this frictional force, which is now kinetic, it's moving. The only one I had static friction was the first one. So let me write down uphill A equals negative 3.9 meters per second squared, or, well, I showed you how to write it in unit vector notation. It's negative, it goes downhill. This is going to be kinetic now, so now C is give it a push downhill. What happens if I start it downhill? Well, starting it downhill, it overcomes static friction, and this is 19.5 newtons. Again, uphill is positive, down is negative. Now we have T plus 19.5 minus 66 newtons equals, it's going to accelerate downhill, negative 10.2 times A. That's kilograms. And then for the blue one, the 3.2, we got T minus 32 equals positive 3.2 A. All right, so these two right here combine to give me negative 46, I believe. So negative 46.5 actually newtons. And I'm going to multiply this bottom one through by negative. So negative, positive, negative. Look, I'm adding these two together again. Again, I get 13.4 kilograms for the total mass. And my net, and it's negative. My net force is going to be negative 14.5, and A is basically going to equal 1.08 meters per second squared in the negative direction. If we say downhill is negative, we write that in unit vector notation. It's going to be negative 1.08 meters per second squared pi. So this is going to be A equals negative 1.08 meters per second squared. The hard part about this question is they make this, let me circle this, they make this a small number and this a big number. So now it's kind of ambivalent. You're like, which way does it go? Well, this number right here is a big number compared to this number. So it, by nature, wants to move and accelerate in that direction. But what they did is they were kind of tricky. They made this static friction so big that it wouldn't move if you didn't push it. And if you pushed it uphill, again, it's wanting to move downhill, it would eventually stop and go back to static friction and not move. If you push it downhill, well, it takes off, but not at a really large rate, about 1 meters per second squared. That's basically what ended up happening. So that is number 27. Sort of a difficult problem. Watch this again if you need to and get a grasp on it. But that's the basic idea behind number 27.